So these are the four equations grouped together, the ones that Maxwell realized described all electromagnetic interactions in classical physics. So although he hadn't derived them all himself, they're often collectively known as Maxwell's laws. Now, when Maxwell started to analyze the last two and look at them in the case where it was a vacuum and where there was no current, he found a family of possible solutions to Faraday's law and the Ampère-Maxwell law. And he found that those solutions were the equations that described a wave. Later, I'll work through and show that the wave equations do in fact satisfy those two laws. So Maxwell announced his discoveries in a lecture in 1862. It was the greatest advance in scientific knowledge since Newton. Einstein later used Maxwell's equations with their constant speed of light in a vacuum as a justification for his theory of special relativity. So these are the equations we're going to use for the electric and magnetic field components of an electromagnetic wave. So they're both sinusoidal waves, and you've seen waves of that form before. We use the same quantities you've seen previously. So k is the angular wave number, which is 2 pi over lambda, and omega is the angular frequency, which equals 2 pi times the frequency f. Now, the speed of a wave of this form is given by omega over k, which is 2 pi f over 2 pi divided by lambda, and that gives us lambda times f, and we know that that is the speed of a wave. So let's have a look and see if they actually satisfy the last two of Maxwell's equations. So we want to work through using the Faraday's law and Maxwell's law to get the wave equation for light. So starting with Faraday, he said that basically when you have a changing magnetic flux, it creates some electric field going around a circle, around a loop of some kind. Now let's look at the case where we've got an area of space here, and we're looking at a rectangle. Now it's dx wide, it's h high, and let's say we're looking at a case where we're moving to the right, and at this point we've got electric field E, but a little bit further to the right we've got a bit more electric field. It's E plus dE. So if the electric field is changing as you move to the right, then we've got some magnetic field at right angles to it. So let's use Faraday's law, and we're going to take the electric field around this rectangle. Now, the only components that won't equal zero are those vertical components where we've got E in the direction of ds. So top and bottom, where we're moving at right angles to the field, it'll be 0. So we'd simply have that E ds is going to be the electric field times that height minus the electric field on the left times the height, and that just is the height times the difference between the fields. And then we've got phi b, which is b times a, is going to be the area, which is h times dx, times b. So d phi b dt is going to be h times dx times db dt. So we've got h times dE equals h times dx dB dt. So that gives us that dE dx equals minus dB dt. So the change in electric field with distance equals the change in magnetic field with time. So in the same way, Maxwell's law that says if there's no current, then we have a B ds equals mu naught E naught d phi E dt, so electric flux. We could go through it and that will just give us a very similar thing, that minus dB dx equals mu naught E naught electric field dt. Now the first thing we're going to do is rearrange this last term and bring dx over this side. And I'll go over the page. So we have dB equals mu naught E naught dE dt times dx. Then let's take dE dx equals minus ddt minus mu naught E naught dE dt times dx. So then we get d2e dx squared by dividing by dx is just mu naught E naught d2e dt squared. And that is a wave equation. If we were to do it as d2e dx squared minus mu naught E naught d2e dt squared equals 0, that describes a linear wave. And in the same way, we could work through and we will get d2b dx squared equals mu naught E naught d2b dt squared, because they're very similar. And so that gives us our second wave equation, d2b dx squared minus mu naught E naught d2b dt squared equals 0. Now the solution to this, I will tell you and then I'll prove it. The simplest solution, at any rate, is the equation of a sine wave, where electric field that is a function of position and of is E naught times sine kx minus omega t. This is our equation for a sine wave. B is also a sine wave, so it is B naught sine kx minus omega t. And we remember that k is the angular wave number, is 2 pi over lambda, and the omega, which is the angular frequency, is 2 pi f. So let's test the equations that we got back over the page. To do that, we need d2e dx squared and d2e dt squared. And then if we can prove it for electric field, we'll know it'll be true for magnetic field. So dE dx is going to be this turned into a cos function, because the derivative of sine is cos, and times the coefficient of x, so it is k E naught cos kx minus omega t. And then get the second derivative. The derivative of cos is minus sine, and again we times it by the coefficient of x, so minus k squared E naught sine kx minus omega t. Now if we're getting the derivative with respect to time, same thing, we times now by the coefficient of t, so it's minus omega E naught, and then we go from sine to cos. And d2e dt squared is going to be again times minus omega, So that would be plus omega squared, but the derivative of cos is minus sine, so we get minus omega squared E naught sine kx minus omega t. So we want to test that this fits the equation d2e dx squared minus mu naught E naught d2e dt squared equals 0. So let's put that in. d2e dx squared is minus k squared E naught sine kx minus omega t minus mu naught E naught times minus omega squared E naught sine kx minus omega t equals 0. So E naughts cancel, sine kx minus omega t cancels. We simply get that k squared minus mu naught E naught omega squared equals 0. So k squared equals mu naught E naught omega squared. So let's prove this. This means then 2 pi over lambda squared equals mu naught E naught 2 pi f squared. So we have 4 pi squared over lambda squared mu naught E naught 4 pi squared f squared. Get rid of that. We simply have, we're going to take lambda over this side and we're going to divide by mu naught E naught. Now we know that V equals F lambda, so that means that V equals 1 over square root of mu naught E naught. Let's put in some values for this. So if V equals 1 over the square root of mu naught E naught, we remember that mu naught is the permeability of free space, and that is 4 pi by 10 to the minus 7 Teslas times meters per ampere, and E naught is the permittivity of free space, the electric permittivity, and that, thinking back even further, was 8.85 by 10 to the minus 12 coulombs squared newtons meters squared. So if I plug this in, V equals 1 over square root of 4 pi by 10 to the minus 7 times 8.85 by 10 to the minus 12. That gives me 2.9986 by 10 to the 8 meters per second. So about equal to 3 by 10 to the 8 meters per second. So that shows that our wave of traveling electric and magnetic field travels at only one speed if it's in free space, and that speed is the speed of light.